Hello, thanks for joining us on Space Nuts, the astronomy and space science podcast. My name is Andrew Dunkley, and it's always good to have your company. Hope you're well. Coming up on this episode, being a divisible by 5 episode, 330, it's all questions. We've got some text questions and some audio questions to go through. 3 of them are focused on the moon, so and very different questions they all are. We've also got a follow-up to the DART mission and a question about virtual matter and what of the future of ground-based telescopes now that we're getting such great technology out into the ether. We're going to tackle all of that today on Space Nuts.
15 seconds, guidance internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2, 1, 2, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And I couldn't do this without Professor Fred Watson, astronomer at large. Hello, Fred.
I'm sure you could, Andrew. In fact, you might do a better job.
No.
Well, it might be, the science fiction show, but that's all right.
That's what it would turn into. Yeah. Well, we'd have to call the podcast BS by Andrew. So I think that would be it.
No,
which is not what Astronomy Daily is all about. That's certainly factual, but it's not me creating the information. I'm just passing it on, which is what I'm generally reasonably average at. Now, how you been? I mean, I've been away, even though we've had episodes continuing. We pre-recorded a whole batch before I went away. So how have you been the last few weeks?
Very well, thank you, Andrew. A few hiccups here and there, a few ups and downs. I've been down in South Australia doing gigs down there, and south coast of New South Wales doing gigs down there. It's been good fun, but and there's more to come, actually. We've got tremendous stuff happening at the end of this month, but it's been fine. And I'm looking forward to hearing about your trip away.
Yeah, I haven't got much time to talk about it today, but I did have a question because I discovered something. We went to Florence, so I saw a statue of Galileo there, which I took a photo of. But when we were in Monaco, I saw an observatory. Are you aware of that?
Yes, it is the observatory in Nice. The Nice observatory.
It wouldn't be in Monaco, but I was in Monaco and I could see it on the top of the mountain.
That's right. Yeah, I've never been. I have, like you've been on the train probably to Monaco, but I did have a colleague who worked there, and she said it was a delightful place to work, as you'd expect. The observatory of Nice. Yeah.
It's a very vertical place.
It is, yes.
Monaco.
Yes, it is.
I know per square metre it's the most expensive real estate in the world, but I couldn't live there because you're going up and down stairs and lifts and travelators and I mean, I don't know how they race Formula Ones there. There is no room to move.
They were last time I was there. They were I think they had the Grand Prix, and they were dismantling all the stands and things, so you could sort of see how it all fitted into the city. But yeah, it was quite impressive.
Yeah, it was. Anyway, it was a fantastic trip, but I'll tell you about it in a later episode.
Sounds good.
Anyway, we'll get back to my holiday some other time when we've got time to talk about it. But we've got an all questions episode today, Fred, and we're going to kick off with a question from Zach in Washington. Now, we've heard from Zach before, but he's following up the DART mission.
Hello, Andrew and Fred. Love the podcast. This is Zach from Washington, D.C. Watched the DART mission broadcast live. Thought it was amazing. The whole mission was great. Fantastic idea to save the planet. I know this mission was a proof of concept, but wasn't the impact asteroid, the smaller one, too small in itself even to have hypothetically done any damage to Earth? Like this mission would be sort of extrapolated to larger celestial bodies that pose an impact. So I'm just kind of wondering about the value. We would probably in the future need to repeat this with a larger payload. Anyways, that's my question. Thank you. Bye.
Yeah, he makes a very valid point, does Zach?
No, he doesn't. Because, Zach, forgive me for that, sounded very cheeky, but the bottom line is that surface, the object that was moved, and it was successfully moved by the spacecraft, is about 170 meters in diameter, and that would do almost continent-wide damage if it hit the Earth. It is a significant object, poses a significant risk if an object that size entered the Earth's atmosphere and then hit the ground. So when you think of it, so the sort of size scales that we've got historical records of are in the region of 50 meters. The Tusker event was probably an object 50 meters or so across. That devastated thousands of square kilometers of Siberian forest. Had it been a city, that would have been curtains for the city. So 170 meters is definitely a potentially hazardous and dangerous object. And it's that scale of objects, that approximate size, that is currently the target of interest for all the various telescopes that are looking for these things. So far, we have found none of that size that would impact the Earth within the next 100 years. But the potential for damage from one of those is significant. So this experiment was not just a proof of concept in the sense, can this be done for asteroids of any size? It actually is a great test of what we might need to do if one of these things turns up. We think we only know about 40% of those objects of that size that would cross the Earth's orbit, whereas when you look up to a kilometre or so, we think we've got most of them. Not all of them, because there are some within the Earth's orbit that are hard to find. There was one turned up last week, 2022 AP7, which was hitting the headlines last week because this is an asteroid which won't actually hit the Earth, but at 1.5 kilometers in diameter, it's the size that we think we're pretty well sure of, that we've got most of them. But because that one orbits within the Earth, it is not yet. It hasn't been found.
We talked about that a month or so ago about, I think there was an astronomer that came out and said, look, we need to pay more attention to the sun for those objects that are orbiting within the orbit of the Earth, because they're a risk as well, because we're looking outwards at things coming in, but there could be things on the inside coming out. And exactly. This is one of them. I must say I saw the headline while I was on holidays pop up from the popular press saying, planet-killing asteroid discovered. And then, of course, the next line said, but it won't hit Earth.
That's right. Its orbit actually keeps it away from Earth, even though the orbit does cross the Earth's orbit. But the asteroids, as I said, it's 2022 AP7. It's in what's called a resonant orbit with the Earth. So every once round for the Earth is 5 times. Sorry, every 5 times round for the Earth is once round for the asteroid. Right. And it's never in the same place. But it is possible that down the track, orbits change if you've got gravitational interactions with things like Jupiter, and that thing goes a long way out into the solar system on its sort of outer side. But yeah, it highlighted exactly what that astronomer said. I can't remember who said that we really need to keep an eye on things inside the Earth's orbit. And the best way to do that is actually with a spacecraft orbiting somewhere at the first Lagrange point between Earth and the Sun, which is a stable point, looking back at the Earth for these near-Earth objects tracking not too far from the Earth within the Earth's orbit. Yeah,
the Sun is a rather pesky thing, isn't it? It's so bright it blinds us from seeing some of the threats to Earth that may exist, and therein lies the problem. But there are ways of getting past that, surely.
With radar and things of that sort, that's right. Radar, you tend to need to know where things are before you can squirt radio waves at them to get a reflection.
That's a fair point. So Zach's assessment of the size of Dolphus was a bit of an underreaction, maybe.
But yeah, that's all fine.
Or overreaction, maybe. I don't know. But so it is a nasty one if it would ever hit us.
Yes, that's right.
Yeah. So Didymos would be worse.
That's 700 meters, I think, or 750. Yeah. But Didymos is big enough that we would probably know about it already.
Yeah.
we do.
Yeah, we do, obviously.
We do.
We've been there,
Even
done
though
that now.
It's actually in the main asteroid belt. It's never going to come anywhere near the Earth. But,
Oh, well, that's good news.
yeah.
But, yeah, we keep an eye out for whatever may develop out there, because there are plenty of sources of asteroids, and it just takes a nudge or a bump or a wink or, under-the-table payment, and it's on its way.
Yeah, and forgive me, I must correct myself. I said that Didymos is in the main asteroid belt. It's not actually. It is one that comes within the inner solar system.
Uh-huh.
But its orbit is stable, and we're cool.
I suppose what we're getting at here is size. When it comes to asteroids, size does matter.
It does indeed.
So how small is small enough for it not to do anything?
2 or 3 meters. They probably come in every week.
Right.
Burn up in the atmosphere, maybe as a fireball or an explosion in the atmosphere.
Yeah.
As you know, though, the event the asteroid that hit the atmosphere above
Chelyabinsk.
Chelyabinsk, that's right, back in 2013. That was about 30 meters across. And look at the damage that did with the shockwave when it hit the ground. Yeah. Indeed,
yes. We got lucky on that one, didn't we?
We did. Yeah.
All right. So, Zach, it does seem that Dimorphos could do some horrendous damage. But you're right. If it's a bigger object, we're going to probably have to find other ways to redirect them, because that experiment probably was just small in the scheme of things. And I think we've discussed the potential for multiple impacts on an object, or painting it white on one side.
Yes, that's true. It all depends on how long you've got.
Yes.
If you've got a long time, then you can do all these tricks.
Yeah, indeed. Zach, lovely to hear from you. Now, we've got an email from Rusty in Donnybrook in Western Australia. Hi, Andrew and Fred. I'm wondering, could dark matter be virtual matter? We know that virtual matter exists, but we have no idea of its matter density. We know that VM pairs are extremely short-lived, but do not exist in great numbers for tiny amounts of time. During that time, if baryonic in nature, they should each have a tiny mass for that tiny time. Baryon particles all have positive mass, so both members of any pair would not cancel with respect to mass. There could be a great deal of mass trapped within the fabric of space as virtual particles, but we have not worked out a way of quantifying it. Dark matter interacts gravitationally with ordinary matter and other dark matter. VM could also do this. There may be a flow of current VM as a result, and this could explain the rotation of spirals and other dark matter phenomena. What do you think? Thanks for the best podcast in the known universe, Rusty. Thanks, Rusty. That's a really interesting theory.
It is. And I'm sort of trying to think about it. So virtual matter pairs are, I am pretty sure that everything of that kind is taken into account already in our assessment of the matter content of the universe. It's true that you're probing a region of space-time that I'm not an expert in, but I'm in a slight way surprised that Rusty has postulated this as an explanation for dark matter, because virtual matter pairs popping in and out of existence permeate the whole universe, not just where normal matter is. And so what I might have expected is Rusty to say, is this an explanation for dark energy? Because dark energy is everywhere. Dark matter isn't. Dark matter is not something that sort of spreads through the whole universe. And we know that it's distributed in a clumpy fashion, just like the galaxies are in the universe. Now, my guess is that what would knock this idea on the head is gravitational lensing, because for that to happen, you need particles. You need something real, not something virtual, and it needs to be clumpy. Otherwise, it doesn't work. You can't just have it popping in and out everywhere. So, imagining something that might, a flow of matter that might interact with real matter, slow, speed up the rotation of spiral galaxies or whatever that is, I don't think that's a goer. Because I think you'd struggle to explain gravitational lensing with this model. And now a particle physicist sitting here might just say, well, it doesn't work anyway because X, Y, and Z, but I'm not one of those. So I'm not going to say that. I'm just bringing my own personal view of this and hope that Rusty acts in the spirit of constructive debate.
You've certainly run the broom over our first two guests today, Fred.
Sorry, folks. Please tune in next week.
It was nice knowing you, Zach and Rusty, and hope you come back again one day. But no, fair enough. I mean, it's a good question to ask. Maybe it was a typo. Maybe he meant dark energy. I don't think so.
Never mind. No, it's good.
All right. Thanks, Rusty. Good to hear from you as always. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, being episode 330, we're just going to carry on with the questions. And the next question comes from, I hope, Trevor, who is also in Australia, in a place called Druin, I think it's called. I'm not sure I'm aware of it. Sorry about that, Trevor. Now I've done it. He says, my questions are about our moon and its similarities to the sun. Our moon appears exactly the same size as the sun in the sky. It rises in the east, it sets in the west, same as the sun. It traverses the northern sky as seen from the southern hemisphere, same as the sun. Its path across the sky changes with the seasons, same as the sun. So my questions are, how common is this within our solar system? Do the moons of other planets exhibit the same behaviour as our moon? How did this affect early astronomers' understanding of the moon and the sun? Did the fact that the moon and the sun appeared to be the same size and behaved similarly help or hinder their understanding of what was going on in the heavens? Many thanks for your podcast. Damn fine question, Trevor.
Yeah,
really like
it's great stuff. It is great stuff. And
better than Rusty's and Zach's.
So the answer to Trevor's question is yes.
All right.
There you go.
And now the next question comes from.
It is the most extraordinary coincidence, and I think it's almost spooky. This is such an amazing coincidence that the angular diameter of the moon and the angular diameter of the sun are essentially the same. They vary slightly, both of them, because the Earth has an elliptical orbit around the sun, so the sun looks slightly bigger and slightly smaller at some times. Likewise, the moon has an elliptical orbit around the Earth, and so the moon looks smaller and larger. In fact, it varies by 14%, which is quite significant.
Yeah.
And that's why we get different sorts of eclipses. Sometimes the moon doesn't quite cover the disk of the sun, and we get an annular eclipse, or a ring of fire, as it's sometimes called. That, as I said, is a coincidence, and it certainly would have exercised the minds of very early astronomers. I think it's one of the reasons why we have religion, actually, because the moon's disk exactly covers the disk of the sun. So periodically, the sun turns to blackness, which, if you didn't really know what was going on, would be a terrifying experience.
I imagine so.
We know, actually, Andrew, that Indigenous First Nations people here in Australia, Aboriginal people, a lot of the Dreamtime stories about the sun and the moon actually indicate that these people did understand. Back to the earliest times, they understood what was happening. The moon was covering up the disk of the sun, and that's an astounding realization.
Makes the flat earthers look even dumber, doesn't it?
Yes, that's right. Well, yes, anyway, that's another story altogether. But so it is a coincidence. And when you look elsewhere in the solar system, yes, there are eclipses by other bodies, the moons of other planets. And you don't have to look very far to find a stunning video taken in April this year of Mars's bigger moons, Phobos, in real time traversing the disk of the sun, seen by the Perseverance rover.
I remember that. Yeah, it was spectacular. It happened fast too, didn't it? It was like 30 seconds.
Yeah, something like 40 seconds or something like that. That's right. Yeah, it's extraordinary. I'm going to show that tonight in a talk I'm giving, because it's such fabulous footage. So they do happen elsewhere, but there is nowhere else where they exactly cover the disk of the sun. The nearest is one of the moons of Saturn, a tiny moon of Saturn, that if you were standing on the upper cloud decks of Saturn, you would see this oval body kind of just about cover the disk of the sun. That's the nearest there is. So it's a remarkable coincidence. And the reason why the sun, the moon follows the sun in the sky, and its path through the sky is similar, that's just because its orbit around the Earth is not very different in terms of its orientation to the orbit of the sun, the orbit of the moon, the orbit of the Earth around the sun. That's in a plane called the ecliptic plane, and the moon's orbit is tilted at 5 degrees to the ecliptic plane. So it's virtually the same. And what that's telling you is that the moon's always going to be roughly in the same region of the sky as the sun is, or following it, depending on the phase of the moon. So, interesting coincidences, interesting stuff, now well understood, except for this curious similarity between the angular size of the sun and the moon. And just one other aspect to this is a temporary phenomenon. In about 300 million years, it won't be doing that because the moon will have drifted away. And so, make the most of it while you can.
Yes,
Go and watch an eclipse.
Yeah, and don't take too long, or you'll never see it again.
Yeah, that's right.
I suppose his question about whether or not early astronomers got an understanding of the moon and the sun because of this weird coincidence is a good one. I imagine, though, being astronomers, they would have really puzzled over it and figured it out quite fast.
Yes, that's right. I think it's the ancient Greeks would have sussed this completely. And knew how to predict eclipses, as other early peoples did as well.
I suppose we are guilty of being ignorant of the intelligence of past civilizations. I mean, I walked the streets of Pompeii a couple of weeks ago, and honestly, I've got to tell you, it was like walking through any town or city that we know of today. The only thing they didn't have was electricity. But for all intents and purposes, it was a city like any other. It was just, old and made of rock. But it had streets, it had footpaths, it had shops, it had houses, it had questionable premises. It had everything that a modern city has. And to walk those streets, just incredible. So don't underestimate the intelligence of ancient civilizations, because they knew what they were doing. We just assume we're better at it than they were, and it's not an absolute, I don't think. And as you said, the indigenous peoples of Australia figured out the moon and the sun thousands upon thousands of years ago.
Yeah, they did.
All right, great question, Trevor. Thank you, and great to hear from you. Now let's go to a question from Judd and Lisa, who are patrons. So thank you for supporting Space Nuts financially. It's certainly appreciated, and we've been able to buy a lot of coffee. So hello, Andrew and Fred. Always enjoy your fascinating podcast. So I was watching an episode of QI recently that mentioned a bit of space junk I hadn't heard before. It said that there is a theory that our moon originated from 12 smaller moons, gradually coalesced into one. Interesting theory. QI isn't my number one source of space fact, so I'll put this to Fred. Any truth to the 13 moon idea? Why exactly 12? Not thousands of smaller asteroids. What did they all? Why did they all? I'm lost my place here. Why did they all completely coalesce into one? I'm trying to read across a widescreen, so I keep losing the beginning of the next line. Wouldn't there be stragglers drifting around like the space junk we've added? what is the most widely accepted theory of the origin of the moon? I think I recall one about a collision with a small molten Earth that knocked a blob that became the moon. Wouldn't want to have been around that day. No, me neither. That comes from Judd and Lisa in Sydney. Thank you for your questions. The moon seems to be a popular topic this week.
Yes, indeed, this is, as you'd expect with eclipses around.
Yeah.
So really the question that's probably the one to go straight to in Judd and Lisa's text, is it? I can't remember. It's an email.
Yeah, it's an email.
Is what's the current most accepted theory of the origin of the moon? And it certainly isn't that there were 12 moonlets. That is one that I haven't come across before, but it sounds as though it is right on the fringes of the currently accepted ideas of how the moon formed. And I'm a bit surprised at QI, but their fact checkers are sometimes a little bit off the mark. And actually, they often get things about the moon wrong. I've noticed that. Yeah, I don't watch QI these days because I haven't time, but when I used to, that was it. Anyway, what is the most widely accepted view of the origin of the moon? And it's exactly as Judd and Lisa say, the idea that the early Earth was impacted by a large object, something the size of Mars, which, when it collided, essentially removed a lot of the outer layers of the Earth and blasted them into orbit around the Earth. So we've got a debris cloud around the Earth, which itself eventually coalesces to form the moon. And one of the main pieces of supporting evidence for that is the fact that the moon and the Earth are basically made of the same rock. There are differences between them, but the bottom line is that most of the material of the moon is the same as the stuff in the Earth's mantle. That's the outer layer of the Earth itself. So that's a kind of strong evidence, which came from the Apollo era moon missions, very strong evidence that suggests that they have a common origin, that they came from the same blob of stuff. And in fact, people are so confident of that theory that we've given that colliding object a name. It's called Theia, named after the mother of the moon in Greek mythology, if I remember rightly. So that's the most widely accepted view. And it would be hard to see how exactly this, the questions that Judd and Lisa ask about the 12 moon idea, why aren't there left over and things of that sort. It would be hard to see how you could make a moon like the one we've got today from a Lego building set of 12 objects. I don't know how that would work at all.
We do currently have 2 moons, though, don't we? There's a small object that's been captured by the Earth's gravitational pull, but it won't be permanent.
That's right. And it's probably a rocket body, I think.
No, I think this one is actually a rock.
Okay.
But it's only tiny. And
these things do come and go.
Yeah. That's what they said. You said there were only slight differences between the Earth and the moon, that being that the moon's actually made of Swiss cheese.
Apparently.
Yeah.
Yep. Mm.
I just thought I'd throw that one in there because it's very important. Very important to be factual.
Yes.
All right. Did we cover all of their question?
I think so. Yes, I hope so. Anyway, thank you very much.
Well, they do pay us, so we want to cover everything.
Yeah, absolutely. Yes, got to get it right.
Yes, indeed. Thanks, Judd. Thanks, Lisa. Lovely to hear from you, and thanks for supporting Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, Fred, to wrap this up, we've got a couple of audio questions, and the first one comes from someone who sends us a lot of questions, and they're very astute. And this one I like because when I played it for you in rehearsal, it tickled your fancy. You went, "Oh, great question." So this is Buddy in Oregon.
Hi, guys. This is Buddy from Oregon again. Just a real quick question this time. I was listening to an episode, and you were talking about how the spin of the Earth doesn't affect time, and I get that. But if we were to somehow reverse the spin of Earth, would that reel the moon in, or would it keep progressing out? Thanks, guys. Huge fan. You guys are awesome.
Thank you, buddy. Look, it's a great question, and Superman has actually done that. But we don't know what happened to the moon. He reversed the spin of the Earth so he could reverse time and save Lois. We all know that.
That's what happened, was it?
Yeah.
Of course, I do remember that. Yes, I think I was there at the time, actually. So it's a great question, buddy. And as with many of these, the answer is it depends. Because, so if you had the spin of the Earth reversed, but the rotation, the revolution of the moon around the Earth continued in the same direction, then I think I'd really need to think about this a bit more carefully. So I'm talking off the top of my head here, but I think you'd reel the moon in.
Oh, right.
Because the gravitational bulge which the moon raises on the Earth would be projected in the direction away from the moon's motion. And so that, I think, would slow down the revolution of the moon. Yeah, it would. It would have a braking effect on the moon. And when you brake an object in orbit, you pull it in. So if the moon kept going in its same direction, but the Earth suddenly spun the other way, we'd pull the moon back.
Okay.
And that would be a very interesting phenomenon. But anything that would reverse the spin of the Earth might reverse the direction of the moon as well, in which case it would still keep drifting away from it.
Yeah, I suppose that would have to be a factor. I mean, I wouldn't imagine it'd haul it in to the point where it would smash into us. Would it?
I don't think so. I think you still get a stable outcome at the end of it. Yes.
So, but I suppose also, I love these what-if questions, if you didn't already know. But if you reverse the spin of the Earth and the moon kept going the way it is now, it would lap us twice as fast, wouldn't it?
Yeah, that's right. Yeah, it would be quite phenomenal, the speed at which it would appear to go through the sky.
And that would have to have a high impact on tides and life on Earth in general.
It's such a counterintuitive thing. It would still go around wanting a moonth, but it would certainly change the way it goes through the sky. It appears to go through the sky with the diurnal rotation of the moon.
See what you've started, buddy?
Started the old brain cells working, buddy, there, I can tell you.
Get you thinking. But I love the question. It's a really good one. And thanks for sending it in. Now, Fred, one more question to finish off this week's episode. And this one's fairly close to home for you. It's self-explanatory too.
Hi, Fred and Andrew. My name's Barry Brook, and I knew Fred when I was a lad living up at Siding Spring in the 1980s. Fred would no doubt remember my dad, Graham Brook, who worked up there as electronics technician for about 13 years at the site. It's always been fun to hear Fred's voice over the last 7 years anyway, during which time I must have listened to all 320 episodes, I think. Anyway, to my question. Given that we're now entering the age of giant ground-based telescopes with adaptive optics like the ELT, and they're situated in ideal, isolated, dry, high-altitude sites, I was wondering if there was any role left to play for existing mid-sized instruments like the UK Schmidt and the 2.3 metre or even the AAT. Do you think they can be upgraded to keep pace or at least continue to fulfil a meaningful scientific role? I noticed that even at Siding Spring there seems to be a recent focus on building smaller specialised instruments like SkyMapper and the Huntsman. Are they the future of the site? Anyway, thanks both, and keep up the terrific podcast.
Thanks, Barry. Lovely to hear from you. There's a little bit of a bolt from the past. Fred?
Yes. And Barry is completely modest because he hasn't mentioned that he's actually a professor himself.
Oh.
And just thinking back, I've run into Barry a few times, over the decades. And it's always a delight to see him. And I do remember his father, Graham, well. I apologise, Barry, but I can't remember what you are a professor of. But I do remember being very impressed with your academic achievements, because I seem to remember you've won some awards as well. These are all locked in there somewhere. So great to hear your question. Great to talk to you. But I think your question's actually absolutely on the money. We've got an era now where the best observing sites for optical telescopes, the best observing sites in the world, are about half a dozen, if that, mountain tops, many of which, certainly many of the southern hemisphere ones, are in northern Chile, where conditions are probably the best in the world for optical astronomy. Some would argue that Antarctica is better.
Okay.
Because they have some excellent conditions there too, but there are other issues that come to play in Antarctica, not the least of which you only see half the sky, and you only see it for half the year.
Yeah.
So they're all issues, but certainly North Chile is where things like the Very Large Telescope, the suite of telescopes that the European Southern Observatory runs, which Australian astronomers have access to now, and the coming ELT, the Extremely Large Telescope, which will be at Cerro Amazones in northern Chile.
And not forgetting the planned HLT, the honkingly large telescope.
Yeah, that's right. Well, we've all got one of those in the back of our minds. I like the idea. Yes, the honkingly large. Yeah. I used to call it the FBT, for the phenomenally telescope, because by then people won't be able to spell. So it's, anyway, that's fine.
And I was about to correct you.
The bottom line is that so the ELT, the European telescope at Cerro Amazones, will be exactly 10 times the diameter of the Anglo-Australian telescope, which has a 3.9 meter mirror. This will have a 39 meter mirror.
Wow.
And that is going to show us things that the AT never could, because, of course, you're talking about very faint objects which come into focus with a big telescope like that. So it's tempting to think that, instruments like this and the current 8 to 10 meter class of telescopes, which are today's workhorses of astronomy, that they might be redundant. And I don't actually know whether that will ever happen. The issue of what you do with these telescopes is reasonably clear cut. Many of the 4 meter class telescopes in the world, and there were several built at the same time as the Anglo-Australian telescope here in New South Wales back in the 70s and 80s, many of those are now...
Oops, sorry.
What are called...
Thought I had that on mute.
With a musical introduction, they are now what you call single-purpose telescopes. So they've got an instrument that lets them do one job, like one that's run by the European Southern Observatory, a 3.6 meter, that has an instrument on that's finding planets. It's called HARPS.
Yeah, I've heard of that one. Yeah.
Yeah, and some of the big telescopes in the northern hemisphere, the 4 meter class, one of them's got a sort of survey type facility on it to measure lots and lots of stars and planets. So these things do compress, rather than trying to be all things to all astronomers, which they were when they were built. The 4 meter class telescopes now generally are single purpose. Actually, the Anglo-Australian telescope is still offering 5 different instruments, and that makes it quite unique in this world, or almost unique. But it comes with a price, in the sense that the economics of this is such that you've got to have a big crew to operate an old telescope with many different facilities. So there may be a time in the future when the Anglo-Australian telescope just becomes a one facility instrument,
a one-trick pony.
Yeah, and that's a nice name for it.
I thought it was insulting.
No, that's fine, as long as it keeps the telescope operating.
As long as it's a good trick.
And it's a good trick. The other thing about these telescopes, certainly in regard to the Anglo-Australian telescope, is that it's on Australian soil. It's not on the most supreme sites in the world. These are in northern Chile, as I said, in the southern hemisphere. It's in a climate where you've got perhaps 2/3 of the nights are clear. You've got not quite the best atmospheric turbulence. It can be very good, but it doesn't match the Chilean sites, and that's the important criterion. But it's in Australia. And what that means is that you've got a workhorse on which people can try out new ideas for instruments. So it's a test bed for new instruments. And that's happened with the UK Schmidt telescope that Barry also mentioned. That's been a test bed for a number of new instruments.
Yeah.
The Anglo-Australian telescope is as well. Plus, it lets you train astronomers on a telescope where they don't have to go halfway across the world. They can use it on Australian sites with perhaps less competition for time on that telescope. So there is a role for them. Now, whether that role will extend more than 20 or 30 years, I don't know. I think perhaps in a decade, people will be looking seriously at some of these telescopes and asking whether they are viable. Yeah. None of the 4-meter class telescopes have yet closed, and that includes another that Barry mentioned, the United Kingdom Infrared Telescope, although I think that's the one that may well be the first to close when it does.
So retrofitting them and updating
putting
them.
New equipment on, that's right.
That may be the option.
Well, that's what's happened. That's why they're still competitive today in an era of 8 to 10 meter class telescopes.
But not a permanent fix. They're ultimately going to reach an end date.
I think that's probably right.
Yes.
Don't know when it will be, though. And it's actually part of my job, Andrew, is looking at the long-term future of the Anglo-Australian telescope and hoping that we can find the money to keep running it for as long a period as possible.
All comes down to money, doesn't it?
It does in the end. That's right.
All right. Thank you, Barry, and great to hear from you, and thanks for your backstory, even though you left out the most important bit, which is your scholastic achievement. But that's okay. A lot of people don't like to skite, and that's fine. Fred did it for you. That wraps it up, Fred. Thank you so much.
It's been great, hasn't it? And welcome back again, Andrew, from your sojourns in Europe, and we'll talk again very soon.
We will indeed. And don't forget, if you've got questions for us, send them through via our website, spacenutspodcast.com or spacenuts.io. There are various ways you can send us questions. You can send a text through the AMA tab or an audio question, or just click on the link on the right-hand side of the homepage and send us your audio question that way. And don't forget, while you're there, to find out about becoming a patron. We've heard from one of our patrons today, 2 of them actually. And we encourage you to visit the Space Nuts shop for no other reason than to laugh at stuff. But while you're there, you can, pick up a nice little prezi for yourself or someone else. In the meantime, it's been great having your company, and I hope you can join us again on the very next episode of Space Nuts. From me, Andrew Dunkley, it's bye-bye for now.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.